Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Hello everyone. In this video, I and my group members will explain about our integrated project for September 2020 and for the three subjects: separation process 2, reaction engineering 1, and process modeling and simulation. So, there are a total of 4 members in our group. Starting with me, my name is Faris Akmal bin Aminuddin. Our second member is Amirah Zahirah Binti Ashmadi. Our third member, Muhammad Hadzril Asyraf bin Azman. And our last member, Lee Kah Weng. Now, the table of content for our video. The first part is the separation process 2. The second part is reaction engineering 1. The third part is process modeling and simulation. And the last part is the conclusion.
Assalamualaikum and hi, my name is Muhammad Hadzril Asyraf and I will be explaining about the overall block diagram and membrane units for membrane separation process in CEB 2063 separation process 2. There are three objectives for this case study. The first one is we have to design a membrane separation process system for the removal of contaminants from the raw natural gas in stage 1 to meet required specifications of purified natural gas before entering the conversion or reaction process in stage 2. The second one is we have to apply our knowledge into the application of membrane in industries. And the third one is we have to develop a membrane including with their membrane materials, types and configuration with justifications. Firstly, we will look at the overall block diagram. We have to construct the overall block diagram and mass balance should be performed in order to find the flux and the selectivity for each membrane unit. The molar flow rate for each stream also can be obtained through mass balance calculations. And this project consists of 3 membrane units as shown in this figure. Before we proceed to the membrane units, we need to consider the conditions and specifications of the components in these two tables. To find the mole fraction or mole percentage, we need to use these formulas given in the slide. The table below shows the specification in mole percent of the components for both feed and permeate stream. Next, we have come up with 5 general assumptions. The first one is the system is in steady state condition. To ease our mass balance calculation, we need to use basis for the flow rate of retentate stream F6, which is 100 ton per day or 3779.94 kg per hour. The third one is a total 10% of feed methane gas lost through permeation process. The fourth one is oxygen and nitrogen gases are not involved in this process. Lastly, each membrane has specific contaminants selectivity criteria, and this is the formula to convert the mass flow rate of F6 into the unit of molar flow rate. After performing mass balance calculations, we will get the value of molar flow rate for each stream and each component as shown in this figure. And to find the molar flow rate for each component existed in the stream, we need to multiply the mole fraction of the component with molar flow rate of the stream. Lastly, we need to perform mass balance calculations as well for each membrane unit in order to find the flow rate and compositions for each stream. These figures show complete sets of 3 membrane units with their own operating conditions. So that's all from me. Thank you.
And now I will continue explaining about the schematic diagram, flux and selectivity. So for the schematic diagram, this is what we did for the separation process part. So the line that we decided on the hollow fiber membrane module is 1.5 meter, while the membrane thickness is 0.0002 meter, while the outer diameter of the membrane module is 0.25 and the inner diameter is 0.2 meter. For permeation flux is volume flowing through the membrane per unit area per unit time. The unit is meter cube per meter squared per second, and it also can be expressed as mole per meter squared per second. So the general formula is Na equals to V over At. The formula of permeation flux for the hollow fiber use is Na equals to Vm per Am per T per Nh, which Am is the hollow fiber membrane area, while Nh is the number of hollow fiber inside membrane module. This is the formula used for the area, Am equals to pi dl. Here is the calculated permeation flux for the 3 membrane units. For permeability coefficient is defined as the transport flux of material through the membrane times with the unit membrane thickness per unit driving force. The SI unit for permeability coefficient is barrier, and this is the formula. Here is the calculated permeability coefficient based on the formula for the 3 membrane units. For selectivity of a membrane is a measure of the ratio of permeability of the relevant gases for the membrane. It can be calculated as the ratio of permeability of 2 gases in binary separation. So here is the formula for selectivity, alpha equals to PMA over PMB. Here is the calculated selectivity for the 3 membrane units. Okay, I think that is all from me. Thank you.
So now, let's move on to the reaction engineering sector. In response to the global demand on a sustainable energy source, we have chosen the methane steam reforming process to transform the purified natural gas into a valuable main product, which is the hydrogen. This is due to the fact that the hydrogen can actually be used as a renewable synthetic fuels. For example, for the hydrogen vehicles, metal refining, power generation, and even fertilizer production. On the other hand, the reactor that we are using for the methane steam reforming process is a catalytic packed bed reactor. The inlet purified natural gas is assumed to be containing no other contaminants but pure methane gas. The inlet stream will be preheated before entering the PBR reactor. The methane steam reforming process is actually an endothermic reaction, and therefore high temperature will improve the further conversion of methane. Furthermore, the nickel-based catalyst we use in this reforming process. This is because of its low cost, high catalytic activity, and the ability to withstand a wide range of temperature. The sizing of the reactor will be around 2 meter in length and 0.1 meter in diameter, with its operating condition of 500 to 900 degrees Celsius and 30 to 40 bar in pressure in order to achieve the 99% of methane conversion. Last but not least, the strategy we are using to maximize the hydrogen production yield is adding the water-gas shift process after the reforming process and increasing the reactor's temperature at constant pressure and then decreasing the reactor's pressure at constant temperature in order to maximize the hydrogen yield. And that's all for the reaction engineering part. Let's move on to the process modeling and simulation.
Hi, my name is Amirah Binti Ashmadi. Thank you for giving me the opportunity to present about my section. My section is about process modeling and simulation, which we need to develop the mathematical model for the reactors. Second is we need to simulate the steady state process by using simulation software based on the process parameters obtained from CEB 2043. Third is we need to validate the simulation by comparing the simulation with the manual calculation from CEB 2043 and provide deviation error between the simulation and manual calculation. Lastly is we need to analyze and discuss the effect of pressure, temperature, and molar flow rate by using function case study in process simulation software and mathematical models. Next, we will proceed to the developing mathematical model. The image shown in this slide is about complete model simulation, which we use Van Robinson as the fluid package. CH4, H2O, CO, and H2 are used as components. We choose heterogeneous catalytic as the reaction. The mole component that is imputed are CH4 S1, H2O is also S1. The temperature is 700 Celsius, pressure is 3500 kPa, molar flow is 557.8 kg mole per H. We choose mixer and plug flow reactor, which this plug flow reactor is replaced as packed bed reactor since we add catalyst inside it. Now I will talk about the deviation error between the simulation and manual calculation. The manual calculation parameters are obtained from CEB 2043 and the simulation software that we use is Aspen ICs. So there are three deviation errors that we can obtain from this simulation, which are conversion, volume, molar flow rate, and temperature. First, conversion. Conversion of CH4 that is simulated is 7.214%, and the manual calculation of conversion is 99%, which results in the deviation error of 92.71%. Next is volume. The volume simulated is 0.171 meter cubic, while in the manual calculation, the volume that is calculated is 2.43 meter cubic, which results in a deviation error of 99.27%. Third is molar flow. The manual calculation of molar flow from CEB 2043 is 1222.75 kmol per hour, while in the simulation, we generated that the molar flow is 3328 kmol per hour, which results in the deviation error of 172.17. Last but not least is the effect of molar flow rate on the reactor performance. The range of molar flow rate was set to be 100 to 600 kmol per hour for natural gas, while 300 to 800 kmol per hour for water, with the step size of 300 kmol per hour. The inlet molar flow of natural gas and water was set to be the independent variables, while the pressure, temperature of product, component mole fraction, conversion at SMR process at PBR01, void volume, and molar flow rate of the reaction at the product stream were set to be the dependent variables. Now, I will proceed to the conclusion. I will talk about the effect of pressure, temperature, and molar flow rate on the reactor performance, which the range of the pressure were set to be between 3000 kPa to 4000 kPa with the step size of 50 kPa. The inlet pressure of natural gas and pressure of water were set to be independent variables, while dependent variables are set to be temperature of product, component mole fraction, conversion at SMR process at PBR01, void volume, and molar flow rate of the reaction at the product stream. Next is the effect of temperature on the reactor performance. The range temperature was set to be between 500 Celsius to 900 Celsius with the step size of 100 Celsius. The inlet temperature of natural gas and temperature of water were set to be independent variables, while the dependent variables are pressure of product, component mole fraction, conversion at SMR process at PBR01, void volume and molar flow rate of the reaction at the product stream. The last deviation error that we managed to obtain from this simulation is temperature. The temperature of the outlet obtained is decreasing from 698.2 Celsius to 604 Celsius. It is proven by the manual calculation that the temperature calculated is increasing. This is because the conditions of the reactor is slightly favored in this endothermic reaction inside PBR01, which results in the decreasing of the conversion percentage.
In conclusion, for this integrated design project September 2020, our group managed to achieve all the required specifications given in the project task, and we also managed to develop a process design for a cost-effective plan that is simple and safe to operate. And we also learned many valuable things during this project. I think that is all from our group. Thank you.